How rare are twin primes compared to other pairs of primes? That's what we're going to consider in this video. Now, twin primes are prime numbers that differ by 2. Typical examples are 11 and 13. 11 and 13 are both primes, and you see the difference is 2. 29 and 31, both prime differences, 2. 431 and 433. 2027, 2029. Now you could have found within this range here, like say under 2100, you could find many more pairs of twin primes, but I just picked out these four to just give typical examples. Now, are there an infinite number of twin primes? Well, the answer, no one has been able to prove this yet. Though a lot of people conjecture that yes, there are an infinite number of twin primes. Now, for a long time, there was even a speculation that gaps between primes get bigger and bigger and bigger as the numbers get larger and larger and larger. But in 2013, Yutang Zhang proved that primes with gaps of 80 million will always be found. In other words, no matter how large of a number you start with, you can go beyond that point and find at least two primes that have a gap of less than 80 million. Now, 80 million seems like a huge gap, and it doesn't seem like that proves very much. But this was the first time anyone was able to conclusively prove that there was some bound on these gaps, that they don't just get larger and larger and larger. Now, he just picked 80 million. He could have made it smaller than this, but he just picked that number when he was proving this. And then soon after, others built on Yutang Zhang's work, and they've proven that prime gaps of less than, I think, around 250 will always be found. Now, that means no matter how large a number you get to, if you go beyond that point, you can always find two primes that will be within 250 of each other. And so now some have proved smaller gaps, like as small as 6 and 12, but actually, in order to do that, they have to use a conjecture which has not been yet been proven. So about 250, at least at the time of this recording, 250 is about the smallest gap that people have proved that actually exists at any point as you get larger and larger numbers. Now, as you're considering prime numbers, they are not randomly distributed. They don't just pop up randomly, but they kind of act and feel like they're randomly distributed. And sometimes you can get insights into prime numbers and into these twin primes uh, by considering the randomness of these numbers. So now let's consider the first 10,000 natural numbers. And there are 205 differences of 2, that's twin primes between primes, 203 differences of 4, 208 differences of 8, 197 differences of 256, 197 differences of 512. Now, these are all pretty close. Now, as you get larger numbers, you would expect there to be more larger gaps than smaller gaps. So let's go to the first 1 million natural numbers. And there's 8169 twin primes, 8144 differences of 4. Again, differences of 4 are called cousin primes, and you'd see the rest of the numbers there. Now, these are all very, very close, from 8144 for differences of 4 to 8273 for differences of 512. Those are all pretty close. That's within 2%. And so this isn't really very much of a statistical difference. Now, you might suspect that these larger gaps are going to start getting bigger. In fact, here you can see the larger gaps, the 256 and the 512. They're slightly larger than the twin primes. So w the question is, will that continue to increase? But now we find something really interesting. Through the first 10 million natural numbers, the most pairs that occur, at least in the ones we're considering, are twin primes. There's 58,980 twin primes, and that's more than all the others. So at least up to the first 10 million natural numbers, the twin primes are the most common, at least of these pairs of primes we're considering out, and I'll clarify that in a few minutes here. So what this is kind of all almost telling us, at least up to the first 10 million, that the twin primes and all these different pairs are really randomly distributed. At least they can be thought of as being randomly distributed so that a gap of 512 or 256 is not more common than a twin prime. Again, if you look at these numbers, there's no statistical difference here. They're all within maybe less than a percent. So therefore, I'm not saying that the twin primes are more common in general, but just that they're at least appearing at the same frequency these other pairs. And so that kind of was almost telling us that if we found a gap of less than 250 will always occur, then it maybe is indicating that we have good reason to believe that, if that means 512, 256, they're occurring. So that means that twin primes are no less likely to occur than any of these others. Now, when I made the list here, uh, why didn't I include differences of 6, 12, and 14? Notice I didn't include those differences between primes. And the reason is these are in a different category. And so, for example, notice the 2, 4, and 6. Now, I've included 6 and 12. Now, look, these are double what the 2 and 4 were. There's the 2 was 58,980. The 4 was 58,622, but the differences of 6 was 117,000, difference of 12, 117,000. So looking at that, you'd say, wait a minute, it looks like the larger gaps, at least the 6 and the 12, are appearing more often, and somehow there's something driving that. But actually, the reason that's happening is that they are simply twice as likely to occur as the 2, the 4, the 8, the what do we have? 256 and 512. And to see this, we want to answer a question, why are there so many primes that differ by 6? And so let's look at what we have. Remember, the only candidates for primes, as we showed in a previous video, are numbers of the form 6n minus 1 or 6n plus 1, where n is a natural number. And so that's why I say for n equal 2, we'll have like either 11 or 13. For n equal 3, we'll have a 17 and a 19. For n equal 4, we'll have a 23 and 25. Again, these are candidates. They're not necessarily going to be prime numbers, but that's a necessary condition for something to be a prime number. It has to be of 6n, form 6n minus 1 or 6n plus 1. Now, in this case here, notice 25 is in the case of 6n plus 1, but it is not prime. But these are all the candidates for primes. Now, if we take a look at this, for primes, a prime can only pair with one other prime to form a difference of 2. And this is really important to notice. For example, 11, the prime number 11, or the candidate prime 11, can only pair with 13 to have a difference of 2. Same 13, it can't pair with anything else except 11 to form a twin prime. So these can only pair with each other. Same with 17 and 19. 17 can only pair with 19 to form a twin prime. 19 can only pair with 17 to form a twin prime. Same thing with these two, even though 25 is not a prime, it would in the position where it would be a candidate, it can only pair with one other number. Same with cousin primes. If for differences of four, like say 13 can only pair with 17 to have a difference of four. Notice it can't pair with nine because nine isn't in a position that could be a prime. And same with 17, it can only pair with 13 to be a pair, to be a difference of four. It can't pair with one, two, three, four. It can't pair with 21 because 21 is not in the position of a prime. Same with 19 and 23. They can only pair with each other to have a difference of four. But now let's look at differences of six. A prime number may pair with two other prime numbers to form a difference of six. I won't go through a whole bunch of, I'll just pick just the two center numbers here. Like, for example, 19 can pair with 13 to have a difference of six. 19 can pair with 25 to have a difference of six. Same with 17. 17 can pair with 11 to have a difference of six. 17 compared to 23 to have a difference of six. So with differences of six, you have twice as many possibilities as you do for twin primes or cousin primes. And I won't show it here, but you'll find the same thing for differences of 12. So why are there so many primes that differ by six? That's because each prime number, there are two possible primes that will make gaps of six. So, and so we would then expect uh, that there are going to be twice as many differences of six as differences of two or four. And again, the same thing with 12. You could make the same argument for 12. So through the first, let's go back here, sorry. So through the first 10 million natural numbers, we have twice as many differences of six and twice as many differences of 12 as we do of 2 and 4. But that's exactly what we would expect if these were just randomly distributed. So therefore, there's really no gaps, at least through the first 10 million numbers, that are appearing with any more frequency than other gaps. So again, what we can speculate from this is that there's just as much chance of having a twin prime as there is of having a prime, a gap of 512 or 256 or any of these other numbers. Now, again, the 6 and 12 are going to be more just simply because there's double the chances. But it's not because the gap is particularly large or particularly small. They just tend to sort of come up randomly, at least have the feel of coming up randomly. Therefore, it's very likely the fact that they've proven that gaps of less than 250 will always exist. That means it's very, very likely that gaps of 2 or 4 will exist forever and ever, no matter how large your numbers get. Again, you may have some other analysis on this. I'm not a number theory expert by any means. That's not my area of mathematics, but it's something to think about. And maybe you have some other ideas, or maybe you've done some other work or can point to something else to show something different in this.